Hello, everyone. I'm Vincent Reverdy. I'm very happy to be here in person after the several years. And today I will talk about compiler, benchmarking, and metaprogramming. I'm a researcher in computer science and astrophysics in the French Alps at the Laboratoire d'Annecy de Physique des Particules, where I help physicists to write better programs. And today, so as I said, I will talk about compilers, benchmarks, and metaprogramming. When preparing that talk, I wanted to show a lot of results, but I realized that there was a lot going on, and making compiler benchmarks is a science in itself. And today I will focus on this part with a bunch of results, but I won't present too many results, and I guess that will be, I will present more results at a later time. But let's go. So there will be a lot of things in that talk, a lot of template metaprogramming. Don't hesitate to ask questions during the talk if something is not clear. So the question that I would like to answer with that talk is, let's say you have two tuples and you want to write a function that combine these two tuples into another one, okay? So a first way of doing that is to write a type trait that will take on the input one tuple and the other and combine them as a type. This would correspond to type-based metaprogramming. There is another approach, which is function-based, where we could write a function that takes one tuple and another, and return the combined tuple type as the return type. And then we could write this helper that would do a decal type on this function. So these are two different approaches, and some libraries implement them in the first way. Some others implement them in the second way. And about when you have a small program, it's not a big deal. But if you are trying to build giant libraries that are based on template metaprogramming to help users, then there is a question of which is the most efficient, and which is the most efficient in particular at compile time, because both of them will end up at the same thing at runtime. And so the question is, which implementation is better? When you are writing normal programs, often you have several implementations possible, and you are testing them with benchmarks. You are testing kernels with benchmarks to decide which implementation is better than the other at runtime. Here, the question will be the same, except that focusing on runtime, we will be focusing on compile time. So wouldn't it be nice if we could just write something like declare a tuple, and then we would say, let's do a benchmark using that tuple, using the tuple sum that I wrote before. And this will do all the work and give you a feeling of how it performs. And the whole talk will focus on how we can make that happen and what kind of results we can expect from such a thing. So the context in which I first came to this question is that, to give a little bit of context, in the lab I'm working and in the scientific community, there is a problem of code complexity that has arisen over the years. And the problem is when physicists and scientists add more and more things to compute, to code, it grows to things that become less and less maintainable because you want to compose everything with everything else. And at the beginning, it's not really a problem, but with time you add more and more functions, more and more types, more and more things, and the composition of all of these things grow more than exponentially. It's a combinatorial explosion. And the problem, if you want to handle the thing, is that you can hire more and more scientists, but their production will grow linearly with time, while you are facing a problem of explosion of complexity. So it would be very nice if we could reduce this complexity going from a product of types and the product of all the combination of possible concepts to a sum of type. And this can be done using domain-specific language that would assemble the little parts of your program for you and build the main thing for you. And in particular, this can be done using embedded domain-specific language. And this is something where you build a language, a mini language, inside another one. And we can do that in C++ using, for example, template metaprogramming. From the user side, it's easier for the user to compose their type. The problem on the metaprogrammer side, it's more difficult to write such a library. And the problem is that how to decide which implementation will be better than the other. So there is a need to test compile time performance against different implementation strategies. And currently, I found very little way, very little ways of doing that. Like there is no many libraries that allow you to do that. And often people do that by hand. So we will see if we can help with that and write something that could do that for us. So the goal, the main goal is to get information to optimize metaprograms at compile time, to decide which one is better than the other. The mean to do that will be to have a way to benchmark compilers against different metaprograms so we can decide which implementation is better than the other. So given that goal and that mean, there is a list of requirements for the thing we want to achieve. It has to be easy to use, effortlessly deployable, because we don't want to import a lot of things. So it has to be very highly portable and compatible with many compiler toolchains. We don't want to write a program per different library for each compiler. It has to be applicable to any C++ metaprogram. So we don't want to have the meta program developers to change too much their code. It has to be as simple as possible to use. And we don't need, there is not a need for a high temporal resolution. We are not aiming to test compiler at the microsecond level. If we get a feeling of, we just want to have a general feeling of what implementation is better than the other. So the approach will be to write a standalone single file meta library that you can just copy and paste and use. It won't be relying on the instrumentation of a specific compiler because we want to do something generic. It will be written in C++ and backward compatible with C++ 17 so that we can see the evolution over the last several versions of compilers. And we will consider that for the timing, we can use external timing tools, like something as simple as Unix time. So in order to do that, the challenge will be the generation of demanding compile time tasks for arbitrary metaprogram. So if we consider a metaprogram M, the problem when you compile is that there is lots of overhead that are not related to the small function you want to compute. Between the parsing and everything that happens in the compiler, isolating the task is kind of difficult. And in many cases, the compile time of M itself is too small to be exploited. So that means that we have a bad signal-to-noise ratio for that metaprogram M. So the strategy we will take will be to increase that signal-to-noise ratio by removing background information, removing the overhead, and trying to amplify the signal as much as we can. So what we will want to do is to loop our metaprogram M over a very large family of types so that we can amplify the signal and have something that takes a lot of time to compile. And if I had to change the title of this talk, it could be like how to torture compilers, because we want to give them the hardest possible tasks given a particular metaprogram. And for the background removal, we will consider that we have the simplest possible metafunction is the identity metafunction given a type or list of type that it will return the first type as it is. And with these two things combined, we can time things and see how the compiler behaves. So one first approach could be to have, one possible approach would be to build a sequence of types, like a very large sequence of types. So a way to do that is to write a type sequence maker that will take some types and generate a longer version of that type sequence. So in terms of implementation, we would generate the indices given a number of types you want, and we would forward the arguments. And what we would do is that, given the arguments, we would copy and paste the same arguments after each other until we reach the given length. I will give an example, and then we can just write a helper function that will call the right thing so that it generates the types. So, for example, using that thing, if we call that, make a type sequence of 7 types given bool, char, int, and double, what it will so if we compile that, it will take some time to compile, but we would like also to be able to see what types it generates, and a nice way of doing that, a very simple way of doing that, is to just call a pretty function with a function of that signature. And if we call metaprint on the resulting type that it builds, then we obtain something like that, meaning that the produced types are bool, char, int, double, and then it starts again, bool, char, int, etc., etc., etc. Okay. So that's the first way of doing things, and then we can see what happens for very large n. So for G++, for GCC, if we put 1024, we will have a problem of template instantiation depth. So the code won't compile. We could change that option so it would compile, but it's a little annoying. So with Clang, it's a little more complicated to make it bug, but if we raise this number very, very high, we have this thing, and it tells us to submit a bug report. And for the Intel compiler, for 512, it tells us that there is a problem with excessive recursion. So this approach is not really, like if we want to really make a task very complicated for the compiler, we can see that we have problem with that approach. So as I said, there is a compiler limitation that comes from the fact that that there is a limit of the number of template parameters that we have. The problem also is that the type sequence leads to type repetition. So that if we want to see how a metafunction behaves given a list of different types, this won't do the job, because we will compile again and again the same metafunction on the same types. So what we could do instead would be to have a sequence of type sequences. And we would start with a sequence of 1 type, 2 types, 3 types, etc., etc. The problem is that it only solves the problem of repeated types, because we now have a list, we now have a type sequence of unique types. But the problem is that we still have this problem of the limit of number of template parameter. And also, it requires a metaprogram to be compatible with type sequence of arbitrary length, because your metaprogram will have to be able to process an input with 1 type, 2 types, 3 types, etc., etc. So instead of doing that, one thing we could do would be to move from type sequences to type trees. So that instead of the type sequence we had before, we would have nested tuples like this, where we would have like a given sequence of types, another sequence of types, then we would go up and then down, etc., etc. And this way, it's nicer because the limit in terms of template parameter count is not a problem anymore. And the nice thing also is that we can decide that all the tree leaves can have the same length if we want to test it against a meta program that takes a particular number of arguments. So the remaining question is the args something. What should we do about it? Like, how can we generate them in a very generic way? And a way of doing that is to generate permutations of types. So this has several advantages. The first one is that we can generate a large number of unique types. Because if we have a list of very quickly, it will grow very fast. The result has a fixed size, as I said, so that we can provide it to a meta program that takes a particular number of template parameters. And the nice thing also is that generating permutation, there are algorithms that generate this permutation using a recursive structure that is totally compatible with a tree structure. So the strategy we will take will be to start from the sequence of types, generate all the permutation of that sequence, and then execute the meta function to benchmark on all the permutations, and then remove the timing taken by the identity meta function. And by doing it that way, we can really put the compilers under stress and try to see how they behave given a given meta program. So how do we implement this? This will take some time because there are a lot of tricks to make that happen. So let's start by the first thing, how to have type sequences, something to replace tuple. That would be compatible with tuple. So a type sequence will be something like a template parameter pack that accepts 0 or more template arguments. In all the following, we'll call a pack a template parameter pack and something that wraps that. And if P, so that means that if P is a pack if it wraps a sequence of types. Okay? So we'll define it with type traits. We could use concept, but the problem is that we want our library to be compatible with C++17 compilers. But we will define it in the following way. So a type P will be considered to be a pack if it has 3 things. If it has a specialization of pack size that gives you the size of the pack, a pack element that returns you a given element in the pack, and pack rebind, who take your pack and replace the existing types that are inside by other types. Okay? You don't need to, with pack rebind, you don't need to have the same number of template parameters. It can be a different number. And to implement that, we will have 3 type traits: pack size, pack element, and pack rebind. So as I said before, pack size will return the number of elements you have in a pack. So it's very simple to implement, of course. Then we have pack element with the given signature, where the first thing will be the index of the element you want to extract, and the second thing will be the pack itself. So given a given index, it will output the type at this index. Given that the index is between 0 and the number and the size of the pack type. And pack rebind will take, as I said, a pack that already has some types and a new list of arguments, and it will replace the thing in the pack by this new list of arguments. And if we combine these things, we can say that something is a pack. So that's a way of detecting whether a type is a pack. If when we bind our pack with only one type, which is void, and we check that the size of this pack will be 1, and we check that the type, when we rebind it with only one type that is void, we check that the first element is void. And by doing it that way, we check that all the functions are implemented. And we can have a simplified definition, which only check for the that the functions are implemented. We could, as I said, we could do, of course, implement that in terms of concepts, but we want it to be compatible with C++17 thing. Another function we can implement is a checker that will check whether something is a pack, if a pack, and if the type we provide is a pack, then we can have several forms where either it just check whether the thing it will do spinae, so that it will just check whether T is a pack, or we can have branch, so that if T is a pack, it will return the first type. If it's not, it will return the second type. And the way we could write a concept would only be this, that would check the 3 different functions I presented before. And then we want to have a pack index to index the thing. So we can re-implement it as it is in the standard library, just to have something independent. So we have this index and make index. We have an indexer, and so it's a little bit of details, but we can have an indexer for that will generate an index sequence given a number of arguments, and same thing with a given number of arguments. It's the same thing as index sequence, but we want something independent for this library. So, and then the question is how to adapt standard tuple to a pack. So to make a standard tuple as a pack, it's very simple because we just have to specialize our 3 functions. So we will say that pack size on a tuple is the integral constant of the size of the number of arguments of this tuple. For pack element, we will just forward it to tuple element. And for pack rebind, we will, given a list of arguments, we will replace the types inside the tuple with the new list of arguments we provided. So this provides us with type sequences for our meta benchmarking library. Given these type sequences, the second thing is how to access them. So one thing we may want to have is this meta function that gives us so it's the same thing as pack element, except that if the index is not included in your pack, it will return the type that you will provide. I won't go into the details. And then something very important to implement the permutation thing will be this pack front and pack back. And what it will do is that you will provide it a pack, in fact, a pack of packs, and a level. And what the thing will do is that it will recursively descend the pack of packs and give you the first element at the given level. Okay? So it's relatively easy to implement because it's just a recursive call where we descend the number of levels. Again, I won't go into the details. And we will have the same thing, pack back, that will give you the last type of a pack of a pack of a pack of a pack, extra. Okay? So now that we have that, we need to have some operation on packs. So the first one we will need is pack truncate that just remove a given number of remove a certain number of types after the. So you provide it the pack, and it will remove a given number of types at the end. Then we will have pack resize that will be like pack truncate when the size is smaller, but when the size is higher, it will add new types to your thing that equal to a type that you provide. Then packappend do the same thing except that it's only with one type. And packswap is maybe the most important for the permutation thing. What it will do is that it will swap two types in your pack of types. So the way it will work is that so we will variably expand our list of types, and it will rebind our pack with different types, and these different types are given by the following thing. When our index is neither I or j, it will return the index itself. So it will leave the current type untouched. If your index is equal to I, then it will return, it will give you the type that was at position j, and if it is at position j, it will return you the type that is at position I. And by doing that, we can swap our types in our packs. And then we can go for finally we can go for permutation. So first, let's look at what a function permute for a standard C++ program would be. So I'm not talking about metaprogramming here. I'm talking about a regular way of generating permutations. So we have this following signature where the first thing is a function that will execute something on each permutation. It can be only like display. Then we will have an array of things, and the thing will start with the size that is equal to the size of the array. In the first case, so when k equal to 1, we invoke the function on our array. Otherwise, we first recursively call the permute function on k-1 with the parameter k-1. And then we do a loop. And in the loop, if k is a pair index, we will swap the element I and k-1. If it's odd, we will swap the elements 0 and k-1. And then we will call permute on after all these swaps have been taken care of. The problem here is that it's a recursive function, but the array is passed by reference, which means that it would be a problem for template metaprogramming because we cannot really remember types along the way. We cannot have like template reference to template arguments. So we need to have a tricky way of implementing that. So what that means is that we are doing the swapping, instead of copying the array in the tree structure that is generated by the recursion, instead of copying the array, every time we modify the array that was the last permuted. And this leads to a structure like this for an array of 3 elements. So it will recursively generate like 3 different calls. And for each one, it will start by the first permutation. And then it will do some exchange from this one and generate this one. And then it will change things on this one and generate this one, extra. The thing that is, this one is not generated by a copy of what was here, but is generated by what happened here. So this is the thing that where we need to have a reference here and not just a copy. So how to implement that using a template metaprogramming? So we will have the following function. So we'll take a pack as an input. The n parameter will be the equivalent of k before. It will be the size of our pack. I will be an index for our loop. And then we will have, for a given level, we will have a pack of packs. And this thing will start by being initialized with having a pack that is empty. So pack rebind without any other arguments just give you an empty pack. So generic permutation. So what we will do is that we will swap the thing. So this is the same kind of swapping in the preceding function. But here, because we cannot use references, we will use this thing, pack back, where this function, as I presented it before, it was descending of the tree. So pack back, we'll take the existing packs that have been accumulated before, and tells you what was the last pack in that list at the lowest possible level of recursion. Then it will call, so it will call the same function with n, with I plus 1, and it will append to the pack of packs the result of the generic permutation function called with the given this pack and n minus 1. So this way we'll generate our tree of different permutations. And this is just a helper function that initialized everything in a nice way. So at a given level of recursion, so this is when the current index of the loop is equal to 0. We need a special thing that will just append the thing where we start to generate permutation. And then at the end of the loop, we say that our current list of pack is the list of packs that were accumulated in our meta loop. And then we have termination functions that says that when we reach the level 0, it will say that our current pack of the given permutation is the one that is passed. And if for whatever reason we reach a level, if we reach the level 0, it will be the same thing. This is the case. This will be called in particular when we have an empty pack as an input. And then we can use the same thing, except this time, instead of generating permutation, we may want to transform this permutation. So given a pack, we want to execute a meta function on this type. So I won't go into the detail, but the mechanism is the same. We descend the tree and we execute our meta function on all our types. And there is a very important thing here, which is the way the meta function is called is by using this invoke meta function thing. So invoke meta function takes as an input a meta function and a pack that is containing your current permutation, which leads to meta functions. So there is a problem in C++, which is C++ is type generic, meaning that we can have these two things coexisting with a specialization with a vector of t, for example. But the problem is that C++ is not kind generic, meaning that you cannot have the two following things coexisting. You cannot have at the same time an entity that takes template parameters and input, which is a type, and something that takes a template thing in your entity. The interesting thing is that you can continue the hierarchy ad infinitum, meaning that here instead of classes, I could put a template of template of template, etc., etc. And every time you will end up at a different level of your kind hierarchy. And these things cannot coexist. So if you want an interface that can deal with all of that at the same time, you need to go through wrappers. So we will have an unwrapper that will unwrap your thing. And if you just want to wrap a type, then the type contained in your type wrapper will just be t. Okay? And we will write the specialization of unwrapper that will unwrap the thing. So if you have a wrapper of a wrapper of a wrapper of a type, this thing will unwrap everything. And we can write the same interface, this time for template for traits, so that you can provide traits as a meta function. So I won't go into the details, but it works the same way, except that this time you instead of providing a type, you can provide a trait. And it does the unwrapper as before. So we may want to use different types of meta functions so that we can execute our thing on different types of meta programs. So the most obvious one is that our benchmark library should be able to take into account traits. It should be able to take into account templated lambdas. So it's something where you have the parenthesis operator, the call operator that is itself templated, and function objects like traditional functions, but also lambdas. So we will write this thing, invoke meta function, with this void here to be able to specialize it using void t in C++17 style. And the invoke meta function will, given a list of arguments, will execute your meta function on this list of arguments. So the first case will be that there is no valid invocation of our thing on the list of arguments. So in that case, we don't provide a type inside the invoke meta function. Second case, we have a trait. So in that case, what it will do is that it will execute the trait it will unwrap the trait and execute it on the given list of arguments. Then we'll have the template call operator, where when we have a templated lambda, so what it will do is that it will pass the arguments into the templated call. And finally, the last thing is just a simple function, and in that case, it will just default to invoke result, which is provided by the standard library. And the simplest case will be type identity, which is given a type, will just return your type. And the way we pass it as a meta function is just by calling this wrap trait thing that wrap the identity meta function. Okay. Now finally we can try to compute things. So what compute permutation will do is that you will give it a pack of things and a meta function, which is by default the identity meta function. And what it will do is that it will generate the permutation, given the pack, and then it will transform the permutation. It will iterate throughout all the permutation, and it will run the meta function on all the given permutation. The reason why we do that in 2 steps is that we want the default case to be, like, we want to be able to isolate as much as we can the step where we execute the meta function so that it appears clearly in the compiler. If we were mixing the two in one step, the compiler could optimize things and we wouldn't have reliable results. So, and computation will, and then we have a computation thing that will just, given a meta function and a pack, will just recognize what is the pack, what's the meta function, and calls it in the nice order. And then, so inside this computation thing, so as I said, what it will take is a pack function. It will take the pack size, which can be different. For example, if you want to shorten if let's say you provide a pack with 4 different types and you want to only run the benchmark with 3 types, you have a way here to shorten it. And what it will do is that it will compute the permutation for the given pack and the given meta function. And the reason why we wrap it into result is that if we didn't wrap it into results, then if you instantiate computation, it will launch the benchmark. The fact that we'll wrap it into an inner class allows you to really run the benchmark when you actually try to see what's in this result type. And then we have the function that actually runs the benchmark, and to ensure that the thing computes the type, what it does is that it returns the hash code of the type ID of your type. And then finally, we can compute several implementations so that it handles very well all the combination of possible parameters. So that you can provide, regardless of the order, you can provide a size, a meta function, and a pack, and it will recognize everything, and it will put everything together and execute the benchmark. The reason we are doing that is that we want an interface, a function interface, so that you can provide traits, you can provide types, you can provide lambdas, you can provide values, you can provide everything you want. You may want. You want to provide pack objects or pack types. It will work with everything. And every time it will delegate the thing to the compute meta function that will actually run the thing. So to make that happen, we have 13 different specializations, and it works. So the input of our thing is a pack P of types, a meta function f, which is by default the identity meta function, and a size that you may provide and that will optionally truncate your pack. And the return value at runtime of your thing will be the hash of the resulting type. And as a side effect, you will have the compile time. But this is just the side effect, and the side effect you want to benchmark, because you don't really care about what the hash value of the type inside your thing. So let's see how it works. So let's say I want to test something on all the combinations of A, B, C, D. So I take a pack which is a tuple, and I want to see how addConst perform on all the possible combinations. And because I want something small, I will truncate. Just for the example, I will truncate that pack to a size of 3. So the only thing, after all these things, the only thing the user has to write is to include metabench to declare 4 different types, and then call this magical compute function that will take the tuple, the addConst, and the number of things you want to benchmark. Okay? You compile, and it will work. What it will generate is this thing. So it will generate all the possible combinations and execute the addConst function in front of it. And this is just a simple example with 3 different types, but very quickly it grows very fast. So let's see now with a tuple sum. When you want to combine 2 tuples to a third tuple with combine arguments. So the way to do that, again, you just call this magic function compute with a tuple of ABC and your tuple sum function. And this will do the magical work, and it will generate that. So a tuple of tuples where you generated all the permutations and it combined the thing. And let's say an example with a function now. Let's say that you have a function that takes a tuple of things as an input, and what it returns is a tuple of vectors of these arguments. Okay? So this time, there are several ways I can call my compute function. One particular way is to call it, again, on the tuple of ABC. And I can provide a lambda that will return given x, it can vectorify x. Okay? And if you do the right thing, and it will generate that. And already here, I don't have even if it's only on 3 types, I don't have the room to print everything. So you can, and this is, again, for very simple meta functions. You can come up with very complicated meta function and it will work the same. And to have a reference timing, it's very easy. You just compute, you just call compute with your tuple, and it will provide you reference timing and how much time does it take to generate the thing on all the different combinations without executing one function. So just a reminder of how the number of permutation grows. So with already 6 factorial, we have more than 720 types, unique types that are generated. And this is very important to have unique types because we don't want the compiler to optimize over same types. And we can have very easily millions of types with already a pack size of 12. The thing here is that most compiler, so if you want reasonable timing, most compilers you can use a number of pack size between 7 and 9, and it will take some time. If you go to 10, it will break most compiler. It will take hours or tens of hours to compile, and it will take I benchmarked the thing. I tried the thing on a machine that had a 128 gigabyte of RAM, and the compilers were using more than that of memory. So this is with something very easy, as I was presenting before. So you just write this single, very simple thing, and it will torture your compiler with the function you provide. And then you can just use time to see how it performs. So one example of application, we might wonder how if tuple performs well and whether we can optimize tuple or not. So tuples in the standard, at least in the GCC standard library, is implemented as a recursive inheritance. But there is another way we can implement that and see how it performs. So one possible approach is to have this pack item class, and what it will do, it will wrap a type with a given index. Okay, so it has an index and it has a type, and there is something then very tricky, which is all the magic happens here. It has an overload of the bracket operator that takes index as an input. And your index here, the trick is that index is not integer, it's a type, okay? So meaning that for each different index, you will get a different overload of your function. And then you can write your something that will combine all these things. So you have this pack base that will, given a list of indices and given a list of arguments, it will combine, it will inherit from all the combinations of indices and arguments. Okay? And it will inherit, so it will inherit from that, and it will inherit, in particular, your operator bracket. And then we, just for convenience, we have this pack thing. We just inherit from pack base and generate and call this indexer for the given number of template arguments. Okay. And then, if we want to make that a pack, we have to specialize for the pack size, pack element, and pack rebind. So there is no surprise for pack size and pack rebind. But here, the way we can do pack element is just saying that we will see what type it returns when we call the function, when we do we build a pack and we call the bracket operator with the type that contains the given index. Okay. And if we compare how this performs compared to standard tuple, for the 3 different compilers, we see that it performs far better. So on GCC, so this is the total compile time. So it includes the overhead and the time it takes for the meta function the identity meta function to compile. So in practice, that means that the improvement is even better than that. But on GCC, we divide the time by so this is for 7 factorial permutations. We divide the time by more than 3. On Clang, it's even more than that. And on Intel, so on Intel, what's funny is that even for 7 permutation, these go way, way higher, and this never terminates. I mean, it should terminate at some point, but I left it compiled for like 2 or 3 hours, and it was not. Intel was not able to reach the end of the program. So we see that so this is just a reminder of how the thing is implemented. So when we implement it in that way to understand like what's going on, so I'm not a compiler writer, but my guess is that the overload resolution has complexity of the logarithm of the number of types for tuples. I mean, for this implementation. And here we are using the overload resolution to take the given pack element. While for std tuple, it does that by recursive inheritance, and it does it linearly. So what's interesting is that it's a good example of what we can do to optimize for compile time. And when you are dealing with very complex program, that's useful information to see how things perform. And with the meta-bench library, it's very easy to see how things perform because you just write, like, the program to benchmark this is literally like less than 10 lines of code. Just call meta-bench, and it tortures the compiler with your meta function. So as we see, it's possible to do way better than standard tuple. And the same thing works also for type maps and type sequence and type everything. The trick is just to use the overload resolution. And then just to come back to our original question, should we use type-based metaprogramming or function-based metaprogramming? So if we have the two different implementation of packsum using a type trait and packsum using like functions, if we benchmark that, we obtain the following result. So this is for 8 factorial permutation. So the reference, it's only on G++. So the reference case to generate all the permutations is about 400 seconds. This is the time for type-based metaprogramming. And we can see that at least on G++ for the given optimization parameter that I chose, the function-based approach takes more time to compile. So again, if you are a library developer that use a lot of template metaprogramming, that's a very useful information when you have to choose between 2 different implementations. One thing also is that the type-based metaprogramming approach is faster and it seems to use more memory, and the function-based metaprogramming is slower but seems to use less memory. And my guess, again, I'm not a compiler writer, I'm very curious of what a compiler writer would say, but my guess is that when you have memorization when you do type-based metaprogramming that you don't have when you have function-based metaprogramming. So that means that here you consume a lot of memory, but you end up being faster. And in the other case, every time you encounter a meta function, you keep re-implementing it again and again. The nice thing here is that we see that by using this kind of tricks, we can do the same kind of implementation we would do for runtime optimization. So we have a trade-off between compile time, between the time it takes and between memory, so a trade-off between time and space. And the same way we do it for runtime programs, here we can do it for meta programs. So as a conclusion, as I presented, so MetaBench is a C++ library to benchmark compilers. You may want to use it if you want to optimize for compile time. It's very lightweight and easy to use. The way it works is that generating all the permutations of pack of types, and it allows to execute arbitrary meta functions on the resulting type. And you can benchmark with external tools. Linux time would work, but if you have other way of timing things, that would also work. So MetaBench allows you to answer questions about compile time. It's a tool to help metaprogrammers to choose the right implementation, choose the best implementation, but also for compiler developers when they want to submit their compiler to very demanding tasks. Sometimes it can lead to unexpected results because there is a lot of hearsay on what is the best way to implement things in template metaprogramming. And the best way of seeing what to do is to just get data and see how it performs in practice. And something I tried also on different versions of GCC, and I can see I saw very good speedups over the last versions of GCC, things that were taking hours before were taking minutes after the new versions. Interesting thing is that with the change can be quite dramatic from a version of a compiler to another version. And there is a properties of the library at this address. It's just a header file. You copy, you paste, and you write your small meta program to execute it, and it should work. Thank you for your attention, and if you have any question of how to benchmark compilers, I will be happy to answer. Yes.
Question from Philippe Gelman. I'm so happy to see presenters using LaTeX. Can you comment on what challenges you faced putting together your presentation?
It's my own package that I developed that is available online. You should go on my GitHub and see there is something to do these kind of things easily.
Hey, thanks for the talk. So interesting. It was interesting to me to see you use the name MetaBench. It took me a while to figure out that this was not the same as Louis Dionne's MetaBench.
I know it.
Okay, good. Glad you're aware of that. And there's dozens of different versions of this kind of thing, and it's totally awesome that I'm not criticizing at all, but rewriting it, this is awesome. More people doing these kinds of things just leads to more institutional knowledge across all of the different people. I'm kind of interested to know, do you have any thoughts on how to start building on this? Because so many of us that do this, I've done this exact exercise several times, actually twice at least. And so many of us are just doing this to goof around, right? Not as our jobs. Mm-hmm. And so the last thing you want to do when you're goofing around is research what someone else did, right? And that's totally fair. There's nothing wrong with that. But in terms of actually using this for real purposes, do you have any thoughts on how we can start building community around this and building discussions around this to kind of combine knowledge across multiple efforts like this?
So that's a very good question. What I think is that it would be extremely useful to have, I think, open data and have data repositories with results where everyone could contribute would be awesome. So that you can see, we can have results and share results and see how different things perform. With the things is that in my particular case, I need that to do metaprogramming on supercomputers, and the first thing, like before implementing my program, I run this thing for a lot of different combinations of parameters and supercomputers that actually takes like thousands, tens of thousands of hours to compute because I want to have something very exhaustive. And it's a shame that there is no way that I can like really share these results apart from like publishing a paper. But that would be very nice to have like something uniform and something that would test all the compilers, and you would just get that like the raw data that you could analyze yourself and do your own plots. So I think that would be extremely like useful for the community.
You want to write it?
I'm planning to write it because I need it.
Hey, I remember two things that you mentioned where you added some code in order to isolate the part that you were interested in benchmarking.
Mm-hmm.
You put a type into a result struct, and there was another place where you did something in 2 steps with 2 sets.
Yes.
So I'm wondering, how did you find those? And
okay.
How do you know that your data is clean, and how clean do you think it is?
I tried so that was based on intuition, on my understanding of how the compiler works. And that was also based on tests where I saw that if I was doing everything in 1 step, I was not getting coherent results. So my best guess is doing it that way. But I would really like to have like inputs from compiler writers, because in the end, it's them who know like how things should be implemented. On that, with the test I run, because I run a lot of different tests, I got very consistent results that I can trust to guide me on optimization of compile time.
Cool. I guess, well, another quick question. How much do you think your machinery affects the times just by being there? Because those permutations are as many types as your instantiation.
Yes. This is the last question I will take. So the question, the question is, how much time does the machinery take? Actually, a lot, because generation, the permutation takes a lot of time. And that's why I have this reference identity metafunction to tell me like, what's the overhead? And this is the function, when I want reliable results, this is the function I benchmark the most to have like good statistics about this function, so that I can then have like good error bars on my results.
Okay, I saw that, but the part after the reference, you still have all of those permutations around in compiler memory. So how much, do you have any idea how much, if at all, that affects the part that you are measuring, just by having those types be in the data structures?
I'm not sure to understand the question, because in practice I don't like, as long as I can tell apart the data I want about my metaprogram and the data that it takes in the compiler, I'm fine. That's the information I need. I hope it answered your question. Thank you, everyone, and have a fun C++ CppCon.